Hello learners, before we answer question 5, I'm going to quickly go through your trig work. And to be able to understand our trig work, we need to look at the numbers that are added, multiplied or subtracted from a trig graph to see how it affects the graph, and that helps you to answer the questions that you require in the examination. They're not on the complicated side, and it'll be well worth your trouble to go over and understand. The first one we're going to look at is a sine graph. So sine graph is your S-shaped graph that looks like that, the first one I'm looking at. And if you talk about its amplitude, we're talking about the distance the graph is away from the center. We use red for that. From here, that's your amplitude. Even if you're looking at it from this point of view, the answer is always a positive one. There is no negative amplitude. Then when you multiply the graph by 2 here, then the graph goes like this. It stretches away to 2, and there's more on the left hand side as well. From the center to there, it's now 2 units. So the amplitude has now become 2 there. And going on to the next one, if you take your sine x and your plus 1 to it, the entire green graph now has just gone up by 1. But the amplitude has not changed from the central point to there, and everywhere else it is just 1 unit still. Then when we came to the purple one now, sine 2x here, something else happened to the graph which we're going to discuss shortly, but the amplitude from the center to that point, wherever you draw it, is 1. Either the top there or the bottom here, it's still 1 unit. So this number in the front of here all over that I'm putting ones in, going from the bottom to the top, is the value of the amplitude. Let me take them all out. We don't want them missing paragraphs, so it's 1 again there. Even here too, the 1 is there, so the amplitude is 1. Or go look in the graph. Look at the purple, the mustard graph. That's the one we're talking about here. We're looking at the black one compared to it, where it went to. Amplitude is 1. From the graph or from the equation, you can give the amplitude. In the last one, you got minus sine x. Even though the graph is flipped over, and you got a minus in the front of here, that makes the amplitude still 1. It cannot be a negative value. It is still 1. Okay, so the number in the front affects amplitude. Most of these are with 1s, except for the blue one has a 2, so the amplitude is 2. Now the period of the graph. Period refers to this, now I need to go with it in a purple color so you can see it. From where we started to where we ended here. That full cycle for one graph is a 360 degrees. So are we doing the answers in black here? 360 degrees. Next one. The blue one again, same story. I'm going over the red like I did before, right to the beginning, right to that point of there. That's where we stop. There's some additional bits within a part of our graph. They were hard to cut off. So it's still 360 degrees. Green one as well. From where we started and to where the cycle starts repeating itself, it is still 360 degrees. Purple one, however, now, this one we need to pay attention. Beginning, and it goes there. Cycle completed. Cut off there. Start again. We're going to that point, a second cycle. So from 0 to 360, we've got 2 cycles for it. We're looking at the purple graph. 2 cycles for it. So you take your 360 degrees and you divide that by 2, and you get that the period is 180. That is how we work with the period. Either looking from the graph or taking this 2 here and using it to do that division and work out the period for both the sine and even the cos graph. In the mustard graph now, you've got period still stays the same, even though the graph shifted from the beginning where it started. Under that movement there, from the beginning where the graph started to where it actually went and stopped is a full 360 degrees. So that period is still 360. Only if we multiply the angle like 2x in the purple one, or multiply any other number there, you divide 360 by that and you get it for sine and cos. Right here as well, red one, looking at the bottom, we started there, we went there, same 360 degrees. So that's about the period and the amplitude and the kind of movements the graphs have, and to answer questions based on this equation. Let's go look at the cos graph now. And the cos graph has a similar story to it. Basic cos graph goes from this point to there like that. Amplitude, if we're talking about it, it's going to be equal to, let's take with the colors, 1. Number in the front is 1, amplitude is 1. Here, the graph is dropped, and if you look from the center to that point or from there to there, it is just half. And where does that come from? Here. That number again helps you to get the amplitude. Looking at this as well, it's 1 from there, or look at the graph. Graph already has information on it. You can see the amplitude there. Right, the purple one as well here. A lot more things we're going to discuss that just now. From the center to that point of there, it is still just 1, and 1 is there as well. So either from the graph or the equation, you can pick up the amplitude. Again here, amplitude is 1, and from the center to that point, it is 1. Mustard again. Notice that we had x minus 45, like in the other one, minus 45. The mustard graph from the original graph went forward by 45 degrees, opposite of that minus 45. And here as well, the amplitude from the center to that point of there is still 1. Even though there's a minus cos, you notice the minus cos, the entire graph flipped over. All the movement is still the same like in the sine graph. Like the green one, you minus 1, it went down. Right, now let's go talk about the purple graph. Now, in this purple graph, I'm just going to open it up a bit more. Pick up another color. Right. If you look at it, it started here at this point. Okay, started at the wrong point there. There's your origin 0 there. Started there and went up there. One cycle. Started again, went to that point, another cycle. Cut off there. And I've already marked it 1, 2, 3 during the video second time. Went to the point of there, third cycle. This is all extras, we're not interested in that. So we have 3 cycles here. So each of them has a period, which has to be the same. So the basic period of your cos graphs are 360 for all the others. If you look at it, 360, 360. But here, you take 360 like in the sine graph and you divide it by this 3. Right, by the 3x from the purple graph. And that leaves you with 120 degrees as its period. Either pick up from the graph or you can solve from the equation. Here again, it's just straightforward 360 degrees, starting point, ending point from, it covers 360 degrees and 360 here as well. Right, check on your movement, the flipping over, what goes up and what moves down, what numbers move it down. When you're adding numbers on the side, moving it up or down, things like that. I'm looking at the green one here, up or down. And this number here in the blue one affects the amplitude. And in the purple one, the number that is being multiplied to the angle affects the period. And then in the mustard one, when you're adding or subtracting by the angle, it affects the horizontal and vertical movement. And in the last one, the minus sign flips the graph over. Right, a little summary of all. Both sine and cos the same. Those things still happen for the tan as well. A couple of minor changes. No amplitude for the tan graph, but the tan graph does have a period. Right, basic tan graph. From 0 to 360 degrees, you can see 1 and then the half to it. Second part and a second half to it. So there are 2 cycles there. Right. So that period from 0 to where the first cycle finished off is 180 degrees. So the period of a tan graph is different. So when you multiply by 2, all that happens is from wherever you had 45 and 1, it now just goes way to 2. Graph just stretches up, stretches down a bit, but the period remains at 180 degrees. Then you take 10 and you add 1 to it. Again, the graph just jumps up 1. Period remains at 180 degrees. No amplitude we talk about here. However, when you multiply it by 2, by the angle, same as what happened for the cos and the sine graph happened. So it was complicated to put the whole thing out here. So I only have a section drawn from 0 to 360. So from the 0 to 360, as I showed you in the first one, we had 2 cycles. Now from 0 to 360, if you count the purple graphs, there's 1, its other half. 2 and its other half, 3 and its other half, 4th one and its other half. So there are 4 cycles. We're not interested in that, but they. So going back to what we have here, shrink it down. We have 4 cycles all the way from 0 to 360 degrees. So if I want to know the period of a graph that was tan 2x, I will need to take 180 degrees and divide it by the 2, which gives me 90 degrees. Right, so every set of 180 degrees has 2 cycles in it, so altogether each cycle of a tan graph there, or period of the tan graph now, is 90 degrees in this example. So only this number here affects the period. Okay, then going on to the minus 45, same as the other graphs. If I said tan x minus 45 degrees, the graph actually went a positive 45 degrees to the right. Again, you multiply by minus sign, you can see from the red, I'm in the last one now, the red graph. Multiply by minus sign, the graph flips over. Okay. You can take note and figure all these out. And again, the period here is 180, just to complete the story. 180 degrees there. And there are asymptotes for these graphs here. In the first one, your asymptote is at, let me just go over in the red so you don't miss the asymptote. Asymptote is here at x equals minus 270, x equals minus 90, then x equals 90, and x equals 270. All the graphs are asymptotes. When you're drawing, you must not touch the asymptote. When we can ask you for equations of the asymptote, as I told you, x equals minus 270, x equals 90, x equals, minus 90, then the 90, and x equals lines. That's what they are. So just do one sample in the middle of all of this here. X equals 90. That's how you write the equation of your asymptote. You could be asked to give them that, you will be able to give that, right? And then when you come to the purple graph, however, you have to look at it a little more closely. where we multiply by 2, we create more cycles. Each one has its own asymptote there, so the asymptotes also change accordingly. Okay, let's go to talk about other things that you asked about the graphs. Domain, which refers to x values. Range refers to y values covered the graph. Turning points, maximum values, minimum values, x-intercepts, y-intercepts. And you need to answer all of those kind of concepts as well. Where f is greater than 0, it's where the graph is above the x-axis. Equal 0, where it is on the x-axis. Usually it's for which x values, so your answer is coming in degrees here. Where x is less than 0, where the graph is below the x-axis. F compared to graph G, where f is greater than G, refers to the region where f is above G, which x values from where to where. Then f equals G is the points of intersection of both those graphs. Let's go on now to answer the questions. In question 6, this is what you have. And the question reads, in the diagram, the graphs fx equals, as I listed out the equation for fx there, and the graph gx, as I listed out here for you, are drawn in the interval of minus 180 to 90 degrees, starting at minus 180 and going to 90 degrees. To redraw the graph so we can figure that out. Photographs don't work very well here. 6.1.1, they ask you for which values of x, common question, for which values of x from that entire domain from minus 180 to 90 will fx times gx be greater than or equal to 0. So if we are multiplying two things and they need to be greater than or equal to 0, we are looking for something about their product. So where are things greater than 0? A positive times a positive is equal to a positive, which is greater than 0. A negative times a negative, which is equal to a positive, that's also greater than 0. So back into our graph here. We're looking for both of them are positive and positive, meaning that I'll just need to look for where they both are above the x-axis or where they both together are below the x-axis, and in that region they'll multiply to give me a positive answer, which is greater than 0. Just looking at the graph, you can see that G is positive all over there. Just looking at the top, positive. So my answer is coming from this value here to that end value there, between that or from in this case, because it wants greater than or equal to. So your answer will be x starting greater than or equal to minus 30, less than or equal to 90 degrees. Or you can write the answer as your interval notation. X is an element of square bracket because including minus 30, semicolon, up to the 90, and square bracket again because you're including that. And added to that, I like to always say x is a limit of real numbers, unless the set was specified otherwise. Then in 6.1.2, they ask you where g of x equals minus 1. This wasn't too bad. Just go to where minus 1 is, read off on your graph, and the answers fell straight into set positions of minus 180 degrees and minus 60 degrees. So x is equal to your minus 60 and your minus 180. Order wouldn't matter which way you put it, whether you're reading it from left or right. Then in 6.2, they asked you if the y-axis is moved to the right, 90 degrees to the right, determine the new equation of f. Now it's very hard to think of now. Delete all these additional things. We've got additional noise too. Right? If it's a little more complicated to take an a y-axis and go move it there and understand it, but you rather think about the graph as moving backwards, and we've studied the graph moving left and right, backwards, forwards, left and right. So your fx graph already looks like this. Scribbles a bit hectic. Is equal to your minus cos x plus 1. So for that graph to end at that y-axis, it needs to move 90 to the left to do the y-axis moving 90 degrees to the right of the graph. So it means the new graph, new fx will be equal to your minus cos. Now what's happening to the cos graph? It is moving 90 degrees to the left in the negative direction. So it becomes x plus 90 plus 1. And this x plus 90 should ring a bell to you from your co-functions from reduction formula. See this pink one here? Cos 90 plus x, or theta in this case here, is minus sign. So now that's what we will change here. Minus into the cos, x plus 90 becomes a minus sine x plus 1. And simplifying this further, we have this equal to minus and minus your plus sine x plus 1. That completes the answer there. discussed already. Right. Now, to be able to do the next question, I need to run you through your solving a triangle. If you have a right angle triangle, you can use SOHCAHTOA. But if you're using A, O, and H in a solution, please put the key down that A, O, and H is actually X, Y, and R, because X, Y, and R is acceptable notation. A, O, and H is what makes our life easy, but they are not acceptable notations in proofs and calculations. Then you have the area rule, sine rule in green there, the cosine rule in blue, and the sine area rule in red. Now, what this green, blue, and red rules do, I'm just going to do little examples for you quickly to help you recall how to use those rules in a triangle. But you don't get straightforward, simple little green, blue, and red triangles to work with like this here. You get ones meshed up in a variety of whole lot of other things. But if you can figure out the triangle, what you learn in these 5 ways of calculating, you can do it in a triangle at a time. Right, the first one I've given you a sample here with 2 angles and a side. To be able to find x now, using the sine rule, it goes like this here. You'll go x over sine 50, the angle that is opposite it, will be equal to, going side over angle, do the same, 20 over sine 25. Cross multiply, and in the cross multiplying, there are some good healthy ways of writing it, 20 into sine 50, so you don't put the 20 into the angle and get a weird answer. Sine 25. If my calculator, or I didn't let myself down and I punch shifting correctly, you should be getting also 36.25. That is it. That's how you use the sine rule. Right, then we go to the next calculation. Now, we're using the sine rule. I'm going to find an angle. You do have, I was supposed to mention this earlier, you need this set up here, arrow shooting the angle. Then you're into the sine rule. Even here too, you've got that. So take the other way now. Right, so now you're going to go sine of angle x over 3. See, now we're choosing the angle over the side because the unknown is the angle. But it doesn't matter which way, you need to be able to do your cross multiplying, flipping over and out properly, mathematically correctly. Right, then we will go sine of 28 degrees over 5. And again, some cross multiplying here will leave you with sine x will be equal to 3 into sine 28 degrees over 5. And do that on your calculator. You should be getting a 0. Let me not put it there. I think the answer is the denominator. And that should leave you with 0.28. Now, having that, now you need to find x. And x happens to be the angle. So x will be equal to sine minus 1, your 0.28. On the calculator, that leaves you with 16.36 degrees. Now, with the sine rule, however, you have to go and do the other option. Or it could be the angle, because sine is positive in the first and the second quadrant, and the second quadrant gives you an obtuse angle. And in a triangle, you can also get an obtuse angled triangle. Must have heard that in some of those years in grade 8. So the other option is x equals 180 degrees minus this first quadrant angle that you found, 16.36 degrees. And we do that subtraction, we are getting the answer of 163.64. But in the second option here, you must check this answer out, because if you look at this 63.64 and this other angle that I have in the diagram, if I add them, we've gone over 180 degrees. As a result, this answer here we'll have to reject, and it is not allowed, or you can write the word reject. Right? Now on to the cosine rule. If you've got side angle side, like look in the picture, 20, 40, and 30 there, whatever measurements you have, you can go ahead and find the x that's opposite those measurements you have there. X squared equals, learn the technique, 20 squared plus the 30 squared minus 2 into the same 20 into the 30, and cos of that angle between them. I'm not writing my cos properly, but I trust you to figure this out, the 40 degrees. And then you don't want the square there, you want x only, then just do that. And one application on the calculator, very carefully, don't make any mistakes, I hope I haven't. You get 47.11 units. By the way, for the sine rule as well, wherever you found measurements, you put units right at the top there. I like to just switch the color a bit over here because it's get boring to the same color. Right, now to find x over here, and the second use of the cosine rule, cos of that angle x will be equal to, watch how we do this over here. You got 3, 4, and 6 in the diagram. Will be equal to the 3 squared on one side plus the 4 squared from the other side of the angle minus the 6 squared that is opposite the angle. All this over 2 into the 3 into the 4. And that's it. Do not go make a mistake and misread it and put some additional unnecessary numbers in there from the top. And you want x, so work this number out of here as to what its value is. I have neglected to do that number. So I'm going to have to just go with the flow. If I stop and start this process again, I find there's a lag in the voice and the writing. So put the number in there, cost minus 1 off that number, and you should be getting the answer of 117.28 degrees. No need to do 2 ways of the answer. That is it. One answer finished. How do we use the area rule? We just shut a little bit over there. The area rule will go like this. Find another color to do it. Go on mustard now. You got side angle, side information like this here, and the area goes like this here. Area equals half into the 3 into the 4 sine of the angle 117 degrees. Once on the calculator, and out will come the area, in this case of 5,35 units squared, or based on whatever was in the picture, meters squared, centimeters squared, etc. If there was any mistakes here and there, please, you can use your calculator and sort it out yourself. All the best in this concept. Right, here's question 5. And this was the 3D diagram that was given to you. And you first need to show that x is equal to 5 over 2 cos theta. Right, a lot. Come to look at my question paper here. Okay. You need to read the question carefully, but everything mentioned in the question is in the diagram. So we shall go straight ahead and start doing 7.1. You need to show that x equals 5 over 2 cos theta. Now that just looks like not fathomable as you stand, but take it one triangle at a time. You've got right angle triangles here, so SOHCAHTOA will work as well. And the top 2 white triangles, they're not the shaded ones, I mean, you've got a AD that's common. Very interesting piece of information. Also, you'll have BD and DC, but AD is of use to us because this is using X and it's using the 5. So those are the 2 triangles we're going to work with. So look at what you have. Try and narrow it down to triangles. Might be spot on, and you can go ahead. Okay, so now what we have here is, let's take the first triangle. Some color in the picture and see which one we're dealing with. This triangle out here, the purple triangle. Draw that one out here. And put the information in. That's A. That's D, that's B, that's 5, that's theta, and that's 90 degrees. So we can use SOHCAHTOA in here. And the best one to use sine because I want to involve the AD. So sine of theta will be equal to the opposite, AD over hypotenuse 5. And now that leaves me cross multiplying across this way, cross multiplying. I will have that AD becomes equal to 5 sine theta. Right, so far so good. Now we shall take another color and go to the next triangle, ADC, right angle triangle involving our x. So if I should draw the triangle first and then work with it. Right, we've got x there, 2 theta at this point, and a 90 degrees there, and ADC. Important to put the labels down so you know we picked up the triangle from as well. Again, sine involves AD. So sine of 2 theta will be equal to AD over hypotenuse x, and another cross multiply will help here, giving you that AD is equal to x sine 2 theta. Right, we've got our 2 ADs here, a value at the top and a value at the bottom. We can equate them and go in from there. But just before we go on, there's no 2 theta in here. So it'd be nice to know from our data sheet, we have this here and use it. So we bring everything to theta. So this leaves you with here, AD will be equal to x 2 sine theta cos theta. So now those two will be equal to each other. We'll have that x, I'm keeping x here because x is going to be on the left hand side and what we need to prove. But if you did it the other way around, a little bit more steps to it, or just maybe one more, not to fuss too much about, you are on your way to getting the answer, will be equal to 5 sine theta. And a lot of this is through practice. You don't know which to start with. That saves you just that small fraction of time. Right, so now divide, we want x only, so divide both sides by, divide your left hand side right by 2 sine theta cos theta. So I'm left with x here equals 5 of sine theta, and what I brought under to divide will be my 2 sine theta, and I can see the answer coming shining through here. Those two cancel out, and we got exactly what we needed, x to be equal to 5 over 2 cos theta. And in the next part here in 7.2, question, let's find it, right? The length of BC is given to you as, calculate the length of BC if it is given that BAC is 112 degrees and theta is 30 degrees. So you want BC, so now we're talking about another triangle altogether. Let's just throw that in red. We're talking about that triangle there. So if I should draw the triangle out here, it's A, B, C. We've got 5 here, and we've got an x over there, and they tell you that BAC is 112 degrees. Ideal thing to do, you need to find this BC here. We can use cosine rule. You may be thinking, how? Because we have x. But we do have, in the previous question, a way of solving that x, having theta. So we need to go ahead and work out that value for x. Take another color. So x will be equal to, make it bigger so you can see it. We had in from our question, it's going to be 5 over 2, look at it again, cos theta. Right, so substitute the 5. Even if you didn't work this out yourself, go ahead and do it. Cos of theta, they gave you theta was 30 degrees, put 30 degrees in there, and you should be getting your answer of 5 root 3 over 2. So now we got the x value. We can do our cosine rule. So we have side angle side in the picture. If you remember your values there, 1, 2, and 3. So BC squared will be equal to, BC squared will be equal to 5 squared plus 5 root, trying to, let me just spread it out so I can write it better. 5 root 3 over 2 squared. I don't think it's going to fit at all. Let me just do that again properly for you. Don't want you to mislearn things. Let's draw a line over here, separating our calculations. BC squared will be equal to 5 squared plus 5 root 3 over 2 all squared minus 2 into 5 into the same 5 root 3 over 2. It's nice to know it like the palm of your hand. And cos of that angle, 117 degrees between them. And then just strike that out there, put your root over it there, and do the whole thing in the calculator, and you should be arriving, I think it's not 17, it's 51, it's 112, sorry, 112 there. What did I write at the top there? 112. And your answer should be 6,64 units. That completes your question 7. Right, I trust this helped you. If not, go over it and make sure you are getting a grasp of insight into how you can answer questions and do well. Thank you for paying attention.